The all-new Tucson has a new communication system called CAN-FD. Then, let's see how this communication was introduced and the history of how this CAN communication has evolved. The history can be divided into three parts. The first communication was applied in BH Genesis for the first time. High-speed CAN and low-speed CAN were applied. Also, the high-speed CAN included C, chassis CAN, and powertrain and chassis controller were integrated in the C CAN. And the low-speed CAN included B, body electrical CAN, and M, multimedia CAN. Later, various functions have been expanded, and the number of controllers increased. The number of controllers connected to one CAN network, therefore, networks were separated with controller characters. The second generation was applied from the DH Genesis, and CGW, Central Gateway, was applied. Existing CCAN had too many controllers connected. Separated depending on the communication characteristics, various types of CAN, such as P, C, B, M, D, H CAN, have been applied. With these CAN communications separated, CGW was applied. Different CAN communications have to communicate with each other. For example, a controller connected to CCAN may communicate with another controller connected to BCAN. However, there are characteristic differences, such as CAN connection speed, waveforms. A module which relays different CAN communication is a gateway. For the first generation communication, specific controller was used for gateway. BCM connected BCAN to CCAN, and the cluster connected BCAN and MCAN. For second generation, number of controllers were increased and more communication networks also got separated. A separate dedicated module, CGW, was applied. Different CAN communications are connected to CGW. CGW acts as a relay when different CAN communication communicate with each other. These days, ADAS and other convenient new technology expanded. Increasing features, the number of controllers and data communication have increased. As a result, it became harder for the existing high-speed CAN communication couldn't handle all the loads. We needed faster communication. That's why we applied CAN-FD at the third generation communication of the all-new Tucson. FD stands for Flexible Data Rate. Flexible data rate means expanded data area from the existing high-speed CAN. With data area of existing high-speed CAN being 8-byte, which is 64-bit, data area of CAN-FD is 64-byte, which is 512-bit. More data can be sent. The data area is increased. Also, connection speed got faster from 500 kbps to 2 Mbps. 2 Mbps equals 2000 kbps, meaning that it got 4 times faster than the existing high-speed CAN. Then, let's compare CAN communication and CAN-FD communication. Average connection speed of the low-speed CAN is 100 kbps. And the average of the high-speed CAN is 500 kbps, 5 times faster than the low speed. The average connection speed of CAN-FD is 4 times faster than the high-speed CAN, 2 Mbps. High-speed CAN was applied in BMDI CAN. For CAN-FD, there are PCAN-FD, CCAN-FD, Extended CAN-FD, with ADAS controller connected. This time, we will measure the waveform using GDS. This is the waveform of low-speed CAN communication. Let's look at the shape of the waveform. For highline, it has an increasing shape from the reference voltage of 0 volt to 3.5 volts. Lowline has a decreasing shape from the reference voltage of 5 volts to 1.5 volts. Overlapping these two, it shows a waveform like this. One frame length is about 1,200 microseconds, which is 1.2 milliseconds. Let's check the highline and lowline of high-speed CAN waveform together. Upper right of the waveform is the highline, rising from the reference voltage of 2.5 volts to 3.5 volts. Below waveform is the low line, falling from the reference voltage of 2.5 volts to 1.5 volts. It has a vertical symmetry waveform. Measuring a frame length, it's about 220 to 260 microseconds. Let's check the CAN FD waveform. It has a similar form with existing high-speed CAN. As the waveform is similar to the existing high-speed CAN, it has similar diagnostic or communication characteristics. For CAN FD communication, it has a difference of data length and transmission speed. However, since consisting elements are similar, it has a similar waveform. It has a similar layout of data start signals, exit signals, data area, arbitration area, etc. Therefore, data length may differ, but since consisting elements are the same, it gets a similar waveform. Also, CAN protocol is the same as the existing one. For reference, protocol is a regulation about hardware and software of communication. Since the protocols are the same, it can be used as the existing CAN hardware. As the hardware characteristics are similar, troubleshooting is also similar. To take a look at CAN FD troubleshooting, let's draw a virtual CAN bus. There are high line, low line, and terminating resistor of 120 ohm connecting two of them. Let's draw the main line. There is another terminating resistor of 120 ohm. Controller is connected at the subline, connected to the main line. A controller is connected, and beside it, B controller is connected. Next, there is a connector. C controller is applied. Connector is next to it. Finally, D controller is applied. For troubleshooting, remove the connector in the middle. If waveform from the A-B controllers are normal, they are normal. Then, the failure will be at the C-D controllers, right? After connecting the corresponding connector, disconnect the connector between C and D controller. If measured waveform from the same side is normal, ABC controller side would be normal. Therefore, the failure will be in the opposite line, or at the D controller. This is how you reduce the failure range. CAN FD troubleshooting is the same as the existing high-speed CAN troubleshooting. Now, let's look at the waveforms of each failure situation. This is when high line is short to power. High line has a constant battery voltage power. Low line has a decreasing shape, showing different waveform from the normal state. This is when low line is short to power. Low line has a constant battery voltage power. High line also has a constant value of about 12 volts, without any special waveform. This is when high line is short to ground. High line has a constant 0 volt value. Low line has a decreasing shape, showing different waveform from the normal state. This is when low line is short to ground. Low line has a constant 0 volt value. High line has an increasing shape, showing different waveform from the normal state. This is when high line is short to low line. Both high line and low line have a reference voltage of 2.5 volts.